Hello everyone and welcome to this video lecture.
Moving forward, now we need to state whether the following statements are true or false. The first condition says that we need to minimize the number of arithmetic operations whenever possible. It is a true statement. Why? The reasons behind minimization of arithmetic operations are efficiency, accuracy, and robustness. Efficiency states that while performing arithmetic operations, it is a computationally expensive process. By minimizing the number of operations required, we can improve the efficiency and hence reduce the processing time of the program. The second is the accuracy. The amount of error by increasing the number of arithmetic operations can be increased. Hence, when we reduce the arithmetic operations, the accuracy of the program also increases. Robustness in a robustness arithmetic operation can also lead to numerical instability and divergence, especially when dealing with large or small values. By minimizing number of operations, we can reduce the risk of numerical stability and make the algorithm more robust. Memory usage memory usage by increasing the number of arithmetic operations, the memory usage also increases. Hence, it also increases the overall cost of building the algorithm. So by reducing the arithmetic operations, we can also reduce the memory usage. Hence, these were the factors which helps to which helps to say that we must minimize the number of arithmetic operations whenever possible. So this is the true statement. The second statement is avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If cannot be avoided, then take the difference before doing other operations. This is also a true statement. For example, now let's take the value of a, which is 1.00000001, and the value of b is 1.00000002. Now we calculate a minus b. As we know, these two are the floating point numbers. While subtracting these, uh, the floating point part, that is 1 and 2, maybe can also be lost due to the limited precision. So it is not recommended to take the difference as early as possible. As written here, in this case, the value of c is very small and may be lost due to the limited precision of the floating point arithmetic. This can lead to inaccurate results and numerical instability, especially if C is used in subsequent calculations. Yeah, because from starting, when we have calculated C from the starting, the error, the error which the error which C have will also be forwarded to the next operations where C is included. Hence, it is not appropriate to divide take the difference of the two nearly equal numbers at the start of the operation. So it is a true statement as well. Now moving forward to the third point, addition or subtraction of number starting with smallest number and works with number in ascending order. This is also a true statement. When adding or subtracting numbers with different magnitudes, it is important to start with smallest number to reduce the impact of limited precision. As we already know that the floating point numbers are limitedly precised. Hence, we need to calculate carefully, and we must be very careful while calculating the floating point arithmetic numbers. For example, we have taken the numbers a, b, c, and d. A equals 1.23, b equals 0.004, c equals 45.67, and d equals 0.0005. If we add this number in the decreasing or descending order, then we will get A plus C plus B plus D, which gives us the answer 46.9035. However, if when we add them in ascending order, that is B plus D plus A plus C, we get the answer as 46.90351, which is more precise. Hence, we should add or subtract the number in the ascending order while we are dealing with the floating point arithmetic. So this statement is also true. The fourth condition is do not formulate an algorithm that tests whether a floating point number equals zero. This is also a true condition. Here we do not recommend it to formulate an algorithm that tests whether a floating point number equals zero, because floating point number are not exact, and mean floating point numbers are not exact and their values may be subject to rounding errors. Means that they are means the with limited precision in floating point numbers, the the value of zero may not be exact. Hence, hence it is difficult to represent the number exactly including zero. This means that even if two floating point numbers are mathematically equal to zero, their representation in memory may be differ due to rounding of errors. So this shows that we should not formulate an algorithm that tests whether the floating point numbers are equal zero. This statement is also a true statement. Now let's move on to the next point, the fifth point. The fifth point states that says that ill conditioning of problems is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way if detect suspected ill conditioning is to alter the parameters by small amount and observe their effect on the solution. This statement is partially true. What this statement is says that ill conditioning means the small changes in the input of the parameter of the problem that can lead to large changes in the output solution. That means that the changes in the input, they are very small in magnitude, whereas the impact they give on the result are very large. These are known as the ill conditioning. So we can detect the ill conditioning by changing the parameters, uh, and testing it out. This is known as sensitivity analysis. If we look over here, one way to detect suspected ill conditioning is indeed to alter the parameters by small amount and observe their effect on the solution. This is known as sensitivity analysis. By analyzing the sensitivity of the solution to change in input parameters, we can determine whether the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. This is one of the ways to determine ill conditioning. Uh, so now let's move to the next part. Uh, Sixth part. The sixth part says that after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, errors grow in each step of the calculation. In such case, reformulate the solution procedure to get a stable numerical algorithm. Statement is also true, or we can say that it is a partially true statement. Numerical algorithms can can indeed lead to numerical instability where error grows in each step of the calculation. This can be due to the variety of factors such as ill conditioning of the factors, uh, ill numerical round of errors, or instability in the algorithm itself. It can be natural as well. To ensure numerical stability, it is important to carefully analyze the algorithm and its implementation to identify potential source of instability. This may involve testing of algorithm on a range of input values, examining the behavior of the algorithm as the input values are varied, and comparing the results with analytical or exact solution where possible. So this is one of the way to test the numerical instability of an algorithm. The solution for numerical stability is to and reformulate the solution and solve it using the reformulated method again. Now the seventh statement is if severe rounding errors are and consequent loss of significant digit is anticipated, and if no alternate formulation to avoid this is possible, then carry more significant digits in the critical calculation using floating point number is in double precision method. In this mode, the length of the mantissa is twice that of the other floating quantities. Severe rounding errors or consequent loss of significant digits can occur in numerical calculation, particularly when dealing with quantities that are widely in magnitude or when performing operations on values that are close to the limit of the machine precision. So the given statement is also true. In so it is a true statement. We can use double precision method. In this method, we double the length of the mantissa, which allows for the twice of the number of mantissa compared to the standard floating numbers. This can help to increase the precision and critical precision of the critical calculation and it reduce the potential of rounding errors to affect the accuracy of the final result. So the above state, so the this statement is also true that we should use double precision method while calculation and in and if severe rounding errors is not allowed or we can't do the severe rounding errors in the problem. Now the eighth statement is double precision require large memory space and slow down calculation. It is also a partially true statement. Double precision would require more memory space than compared to the single precision. Each floating point number is required around 64 bits in double precision as compared to 32 bits in the single precision. However, whether or not double precision slow down calculation depends on the computation of algorithm as well. It is not necessary that it would the slow down the algorithm drastically. It depends on the computational requirements of the algorithm. Uh, in some cases, as we have above seen, in the seventh case, that rounding errors and consequent loss of significant digit can be controlled using double precisions. So the requirement of double precision is also there. So in some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. So double precision also helps in reducing the numerical instability caused by the rounding errors. So this way double precision also helps in making the algorithm more accurate. So double precision requires large memory and slow down calculations, but it is also an important part of the algorithm analysis and is also required. So the above statement is partially true. Now the ninth statement says that we need to calculate in the third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method the relative error. We need to calculate the relative error in this case, and the relative error that comes out is 0.0013. So the Newton-Raphson method state that x n plus 1 is equal to 0 x n divided by 2 times x n. The Newton-Raphson states that x n plus 1 is equal to 0.5 into x n plus 5 divided by x n. So now we assume that the starting point is 7 which is given over here. So x0 is 7. Now we calculate the value of x1 which would be equal to 0.5 into 7 plus 5 by 7 which gives the value 3.07143. Now similarly we calculate the value of x2 which is equal to 0.5 into the value of x1 which is 3.07143 plus 5 divided by 5 divided by the value of x1 that is 3.07143. 0713, which gives us the value 2.2362. Now we calculate the relative error. Relative error can be calculated by xn plus 1 minus xn divided by xn plus 1 whole mod. So we calculate over here using x3 minus x2 divided by x3. We got the values over here. On further solving, we get the values of x3 as 2.24119. Therefore, the third approximation of square root of 5 numerical using Newton-Raphson method is 2.24119. 2.24119. 2.24119, and the relative error here comes out to be 0.0113. 0.0113, as we can see over here, the relative error here is 0.0113 over here. Here the relative error is 0.0113, hence this statement is also true. It with a green color. So this statement is also true. So now moving forward, we move on to the last statement. The last statement says that, just a moment. The last statement states that the iterative methods are computed on the following parameters: the rate of convergence, the amount of computational effort per iteration, sensitivity of the methods to starting values, and the intermediate values. Now let's check for the first point, the rate of convergence. The rate of convergence refers how quickly the iterative method converges the desired solution. The faster the rate of convergence, the better the method. As we all know that the Newton-Raphson method is the method at best method at the rate as the rate of convergence for it is 2, and then we have got the iterative method. So the a statement is a important condition required for iterative method to be compared on the following parameters: the amount of computational effort, it refers to the amount of computations required to obtain the next approximation in the in values. Using this method, the amount of computational efforts per iteration are required. So this statement is also required. The first one is also required, and the sensitivity of the method to the starting value of these intermediate values. This refers to how sensitive the method is to the initial guess and the intermediate value used in the iterative process. A method is less sensitive to initial guess and intermediate. This is also true for the iterative methods. So all the A, B, and C conditions are required parameters for the iterative method to be compared. Hence this for this all three statements are all required. Hence it makes the 10 statement true as well.